So lately I've been working on an open source project designed to build and test models of large-scale structure formation. So just like the CMB has open source codes like CMB Fast and CAM, class, where you can have a particular science target of interest, like say neutrino mass, and then change one particular piece of the code and swap out the feature of interest, and then use the rest of the code base in order to propagate that through to, say, the CMB temperature multipoles. So I'm designing Halotools to be able to do the same thing for large-scale structure observables. So in this case, the observables would be like two-point galaxy clustering, galaxy-galaxy lensing, galaxy groups, void statistics, pairwise velocities, anything you can compute in a mock catalog in a periodic box. Okay, so the idea is to be able to pick your science target of interest. So I'll talk about how this works with assembly bias. And then build a model which has the feature of interest in it. And then to be able to use Halotools to generate a Monte Carlo realization of your model in a simulation. And then compute your observable signature of interest to be able to constrain the model. And to be able to do that at Monte Carlo runtime speed. So you can actually run proper likelihood analyses to be able to constrain these parameters of interest. Okay. So once we open up the sort of parameter space in order to be able to do galaxy halo modeling, depends on more parameters than just halo mass, rapidly the complexity that you can encompass with your model becomes such that a single person cannot reasonably, in a reasonable amount of, say, tenure stream faculty time, actually perform all of the calculations that are necessary, right? So what actually makes Halotools a substantial amount of labor difference than sort of calculations you would do on your laptop and never show anyone the code is that it's all documented, and the test suite is itself documented, and it's intended to be able to have tutorials and guides for how to actually do this yourself. Okay. So what I'll just walk through is just how this sort of exercise works for when your science target of interest is assembly bias. Andrew covered a lot of what I wanted to cover to motivate assembly bias as being something that we absolutely must take seriously if we want to be able to make credible arguments that we can do anything with large-scale structure observables, even in the quasi-nonlinear regime, and actually provide anything besides confirmation bias. Okay, so the standard sort of logic that is unfortunately common for arguments that we don't need to worry about assembly bias is as follows. So I assume that I have an HOD which depends on only mass, and then that allows me to run a fit on, say, clustering data. And then I can indeed fit the clustering data. And then I conclude, well, therefore, assembly bias couldn't be too much of a problem, right? Because otherwise I wouldn't be able to fit the clustering data. Okay, so this is a non sequitur. It's a conclusion that does not follow from the provided evidence, right? So Andrew showed a very specific example of how you can get a perfectly good fit to the data, and you can be radically incorrect about the quench fraction of satellites as a function of halo mass, a very basic target in galaxy evolution. Okay, so yeah, if your science target is galaxy evolution, you can be off in this elementary statistic, and likewise for cosmology. I don't see how we could plausibly be able to say that we have a large-scale structure campaign where we have run constraints on cosmology, detected non-vanilla lambda CDM, and then to be able to make an argument to the community at large that the answer is not actually just that we've made a hard, unmotivated assumption that galaxies have no knowledge of anything besides the mass inside of an imaginary radius. It's an obvious target for what an alternative broken assumption would be as opposed to non-vanilla lambda CDM. Okay, so I think this is absolutely necessary to do, and I don't see any other way around having to forward model the problem. Right, so some of the things that Sahud was talking about, I think, can just be answered just by direct forward modeling, right? So we can look at a signal and kind of eyeball as to whether or not it looks like maybe there's projection effects at work, or we can actually just build models, build them fast enough and compute observables fast enough to where we can actually run likelihood analyses over them, say run RedMapper over these models, and then just constrain whether or not this particular observable statistic of interest is sensitive to assembly bias and whether it reveals it. I don't see a way around this conclusion. Okay, so that's one of the main features of interest, at least in the short term for me, for what I'm doing with Halotools. Okay, so here's the basic idea for how this works. So it's an object-oriented platform, and what this lets you do effectively is to, say, build a wagon that is a composite model for your galaxy distribution, and then just to take the wagon wheel and swap it in and out with one feature of interest. Right? So what I'll walk through is how that swapping off of the wagon wheel works for assembly bias. I will be using the decorated HOD in order to model assembly bias. So this is what Andrew was touching on towards the end of his talk. And the decorated HOD is just exactly like the ordinary HOD in every respect, except that you modulate the abundance of, well, in Andrew's case, the abundance of central galaxies, say, is a function of both halo mass and their potential well depth. And in the case that I'll describe and give a few examples of, what you're going to modulate is the red fraction as a function of halo mass. Okay, so the way that works is the ordinary HOD, just like a standard mass-quenching only HOD, gives you the red fraction as a function of halo mass. And at a given mass, the red fraction gets a boost if you have, say, an old halo. And then, depending on what you call an old halo or a young halo, this is what Urs was pointing out, you can solve for the exact amount that you need to have a decrement in the red fraction in the young halos, such that you get, for the mass-only result, you get the exact same red fraction as a function of halo mass. So in this way, the parameters that you introduce are just how much of a boost do I get to the red fraction as a function of halo mass, right? And then if I take all of the halos at that mass, I have the exact same red fraction, right? So no difference in the mass quenching. But old halos have a preferentially red population. So in this way, the new parameters that you introduce are just formally independent from the standard HOD. So as you run a likelihood analysis on these parameters, well then as you constrain the value of that boost, you're constraining the pure influence of assembly bias on the galaxy population. Okay, so you have a minimal expansion of the parameter space, and the new parameters that you interest are exactly the new things that you want to study if you're interested in assembly bias. Okay? So here's 3 different wagons that you can build, which have different effects for, say, the red fraction as a function of halo mass. So there's standard, standard HOD mass quenching, in which you just have a red fraction as a function of halo mass, and that's coupled independently with the stellar to halo mass relation. So models like this go back at least as far as Frank's paper in 2003, possibly earlier, I don't know. All you do is you have a stellar to halo mass relation, and then in addition to this, you have some fraction of those galaxies are red. And those are independent things. So then you take those 2 wheels and you put them together, and then that's your composite model. So Jeremy took a different approach a couple of years ago, in which he fit Cosmos data having a distinct stellar to halo mass relation for red and blue populations. Okay, so in other words, first you model what the red fraction is as a function of halo mass for central galaxies, and then depending on whether your central is red or whether it's blue, it has a different stellar to halo mass relation. Okay, so finally, you can use this assembly bias decorator. So you can decorate your initial wagon wheel with assembly bias using the decorated HOD. And you have a red fraction as a function of halo mass, and then in addition to that, you preserve that exactly, and you introduce new parameters which then decorate that red fraction. Okay, so all of these 3 sort of classes of models are qualitatively distinct from one another, and they make different predictions for the red to blue cross correlation and the autocorrelation differences. So what Halotools lets you do is to actually work out specifically what the different observable statistics are for different models for this galaxy halo connection. So here's an example. So this is the difference in the red to blue clustering strength normalized by the galaxy clustering for the entire sample. And as you can see, what assembly bias decoration does relative to the underlying standard HOD is to increase the separation between red and blue galaxies, right? Because you're introducing an additional dependence on the clustering, which separates the old and the young. So that's above and beyond mass. And likewise for the cross correlation, now the decorated HOD, what it does is red things now avoid red things now avoid blue things, right? So you have a decrement in the cross correlation. Okay, so what this lets you do then is to study the specific signatures that a given science target of interest, in this case assembly bias, imprints on a given statistic. So I've just focused on 2-point clustering just because that's a very simple and familiar exercise, but you can use the code to compute anything that you want in a mock catalog, anything that can compute in a periodic box. So you can then tailor your statistic for a given science target, specifically designed so that you can come up with the best constraints for the set of parameters or for the kind of model that you're interested in studying. So that's the basic program here. I just focused on assembly bias, the ability to be able to rapidly generate mock catalogs and high-resolution simulations has many other applications that are relevant to both cosmology and galaxy evolution. Exploring these many model degeneracies, which I think threaten our ability to be able to make concrete statements about what we can actually infer about the galaxy halo connection from HOD modeling of 2-point statistics. Systematically testing fitting function approximations, being able to explore a wide different variety of alternative statistics, and also because the code base is written such that it can swap in and out simulations just by passing in the different string that tells you which simulation you're interested in populating. Well, then the exact same code with almost no changes can be used to compute covariance matrices if you have a suite of n-body simulations. All you do is just run a simple loop over the same exact statistic, looping over the different simulation boxes that you have. Okay, so that's the program. I think with that, I'll just conclude.